Look at a photograph of a cargo ship from the 1970s and compare it to a modern container ship from today. The differences are striking. The old ship has a distinctive bridge structure rising high above the deck. The old ship has numerous cranes and loading equipment scattered across the deck. The old ship has a relatively narrow hull compared to its length. The old ship has a large propeller visible at the stern. Now look at the modern ship. The bridge is positioned far forward on the hull, almost at the bow. The modern ship has no visible cranes or equipment on the deck. The deck is completely flat, a vast expanse covered only with containers. The hull is much wider relative to its length. The propeller is enclosed and invisible. The two ships look like they come from different eras. They do. And the differences aren't just cosmetic. They represent fundamental changes in how ships are designed, built, and operated. Modern ships aren't built differently just for aesthetics. They're built differently because of changes in economics, engineering knowledge, materials science, and maritime requirements. Today we're exploring why ship design has evolved so dramatically and what those changes reveal about how technology and human needs interact to drive innovation. To understand why modern ships look different, we need to look at the history of shipbuilding. For thousands of years, wooden ships were the only option. Wooden ships had severe limitations. They couldn't be very large because wood has structural limits. A wooden ship that's too long will sag in the middle. Wooden ships' throttle is not constantly maintained. Wooden ships were slow. The largest wooden ships ever built were only around 300 meters long. In the 1800s, iron and steel replaced wood. Steel ships could be much larger. They could carry more cargo. They were stronger and lasted longer. Steel ships could be faster because engines became available. The transition from wood to steel was revolutionary. But even as ships transitioned to steel, design remained relatively conservative. Ships in the early steel era were still designed with concepts inherited from wooden shipbuilding. The bridge was positioned high on the ship because that's where it had always been. Numerous small cargo handling cranes were built into the ship because that's how cargo had always been loaded. Ships had complex structural designs that reflected wooden ship construction. These design choices made sense at the time, but they became limitations as containerization changed the shipping industry. The container revolution happened in the 1950s. Before containers, cargo was loaded loose into the ship's hold. Longshoremen manually placed each item in the hold. Loading a ship took weeks. Unloading took weeks. The ship spent more time in port than at sea. Containers changed everything. Cargo was packed into standardized metal boxes before arriving at the ship. The containers were stacked on the ship in a grid pattern. Loading a ship now took days instead of weeks. Unloading took days. The ship spent vastly more time at sea generating revenue and less time in port. This shift made the speed of loading and unloading critical to profitability. Container ships were designed from the ground up for containerization. The deck became a simple flat platform for stacking containers. The cargo holds below deck became simple rectangular spaces for more containers. There was no need for cranes on the deck because port cranes would handle the containers. There was no need for complex cargo handling equipment because containers were handled identically, regardless of their contents. This simplification was revolutionary. Modern container ships are essentially floating boxes designed to carry other boxes. The bridge position changed in modern ships because of containerization. On old cargo ships, the bridge was positioned high because the captain needed to see the cargo handling operations on deck. On modern container ships, the cargo handling is done by port cranes, not by ship-based equipment. The bridge doesn't need to be positioned high anymore. Modern designers realized they could move the bridge forward. By positioning the bridge near the bow, the stern becomes completely clear for cargo. This maximizes cargo space. The bridge position also improved because the forward position allows better visibility for navigation. Modern ships have better visibility and more cargo space because of a single design change, bridge position. Hull design has changed dramatically. Old cargo ships had relatively narrow beams compared to their length. This shape reflected the needs of older cargo that fit efficiently in narrow holds. Modern container ships have much wider beams. The wider hull allows more containers to be stacked side by side. A wider hull can carry more containers in the same length. The wider hull also provides better stability because the wider platform is harder to tip. Modern container ships have length-to-beam ratios around 7 to 1. Older cargo ships had ratios around 10 to 1 or higher. This change in proportions is fundamental to how the ship carries cargo. The bow design has evolved. Old ships had relatively blunt bows that pushed water aside. Modern ships have finer bows that cut through the water more efficiently. The bow design reduces wave-making resistance, the energy that's wasted in creating waves. A more efficient bow means the ship requires less engine power to move at the same speed. Less engine power means less fuel consumption. The hull shape above the waterline has also changed. Modern ships have more flare, meaning the hull curves outward at the bow above the waterline. This flare keeps the bow relatively dry in rough seas. The flare also allows more containers to be stacked higher because the wider shape above the waterline provides more space. Propulsion systems have fundamentally changed. Old ships often had reciprocating steam engines that were massive and inefficient. Later, ships transitioned to diesel engines. Modern ships have enormous slow-speed diesel engines that are incredibly efficient. But the propeller itself has also changed. Old ship propellers were relatively simple designs. Modern propeller designs incorporate sophisticated hydrodynamic optimization. The propeller blades might be shaped to match the water flow from the hull precisely. Some modern ships use propellers with special blade designs that reduce cavitation and noise. The relationship between propeller design and hull design has become increasingly sophisticated. Automation has changed ship operations. Old ships required large crews. A large container ship from the 1970s might have needed 40 to 50 crew members to operate the ship, maintain the engines, handle cargo, and provide services. Modern ships of similar size operate with crews of 20 or fewer. Automation has eliminated jobs but has also made shipping more economical. Modern engines have computer controls that optimize performance. Cargo handling doesn't require crew members because port cranes operate remotely. Navigation systems are largely automated. Fewer crew members mean lower operating costs. The ship's design reflects this automation. There's no need for crew accommodations that old ships needed. Modern ships are designed for minimal crew. Structural design has changed because of improved understanding of forces and better materials. Old ships were designed with heavy structural frames at close intervals. The entire interior of the ship was filled with structural steel. Modern ships use more efficient structural designs that place material only where it's needed. Computer analysis allows designers to calculate exact stresses and design the structure precisely to handle those stresses. This means less structural steel is needed. Less structural steel means less weight. Less weight means better fuel efficiency. Modern ships carry more cargo per unit of fuel consumed than old ships because of more efficient structural design. The cargo holds have become simpler. Old ships had cargo holds with irregular shapes designed to fit various cargo types. Modern container ships have cargo holds that are perfectly rectangular. The rectangular holds exactly match the size and shape of standard containers. There's no wasted space. No cargo needs to be specially configured to fit. The simplification of hold design reduces construction cost and complexity. Simple rectangular shapes also allow containers to be stacked efficiently without gaps. Welding technology has changed everything. Old ships were largely riveted. Rivets created joints that were relatively weak and required maintenance. Modern ships are welded throughout. Welded joints are stronger than riveted joints and don't require maintenance. Welding technology has improved dramatically since the 1970s. Modern welding equipment can create perfect joints that are as strong as the surrounding material. Laser welding and other advanced techniques allow construction to be more precise. Better welding means stronger, longer-lasting ships. Compartmentalization has improved. Old ships had watertight compartments, but the compartments were relatively large. Modern ships have many compartments to provide redundancy. If one compartment is flooded, the ship can still float and be salvaged. Multiple compartments mean if a collision or grounding damages the hull in multiple places, the ship doesn't sink immediately. This redundancy has been formalized in maritime regulations. SOLAS, safety of life at sea. Regulations require specific levels of compartmentalization. Modern ship design incorporates compartmentalization as a core principle. Environmental regulations have driven design changes. Old ships burned heavy fuel oil and didn't care much about emissions. Modern ships face strict regulations about sulfur emissions, nitrogen oxides, and carbon dioxide. Ships now have scrubber systems that clean exhaust gases. Some modern ships burn marine gas oil instead of heavy fuel oil. Some experimental ships use liquefied natural gas. These environmental requirements add cost and complexity, but they're mandatory. Ship design has adapted to accommodate these emission control systems. Double hulls are now standard. Many older ships had single hulls with ballast tanks. If the hull was damaged, water could flood the cargo holds. Modern ships have double hulls. The space between the inner and outer hulls provides double protection. If the outer hull is damaged, the inner hull still contains the cargo. The space between hulls can also serve as ballast tanks. Double hulls add cost and weight, but they're now mandated by law for tanker ships and strongly recommended for cargo ships. Double hulls were invented because of oil tanker disasters. The regulatory response was to require structural changes. Power generation has changed. Old ships had large generators driven by the main engine. The generators only produced power when the main engine was running. Modern ships often have separate diesel generators that can run independently. This provides power for the ship when at anchor or when the main engine is shut down. Some modern ships are experimenting with hybrid systems that use batteries and electric motors for efficiency. As batteries and electric propulsion technology improves, more ships will likely transition to hybrid or fully electric propulsion. Fuel efficiency has become a central design goal. Old ships were designed without much consideration for fuel efficiency. Fuel costs were relatively low. Operating costs were dominated by labor. Modern ships are obsessed with fuel efficiency. A reduction in fuel consumption of even 1% saves millions of dollars over the ship's lifetime. Every design decision is evaluated for its effect on fuel consumption. Hull shape, propeller design, engine efficiency, structural weight, even paint schemes are optimized for fuel efficiency. The ship's design is fundamentally different because fuel efficiency is a central design criterion. Materials science has enabled new designs. Old ships were made of carbon steel, plain mild steel. Modern ships use high-strength steels that are lighter and stronger than mild steel. Advanced composite materials are being used in some applications. Aluminium is used in some ship structures where weight is critical. These advanced materials allow designs that weren't possible with older materials. The structure can be lighter while remaining strong. The ship can carry more cargo with the same weight. Computer-aided design has revolutionized ship design. Old ships were designed using drawings and physical models tested in water tanks. Modern ships are designed using sophisticated computer models. The computer can calculate how the hull will perform at different speeds and in different sea conditions. The computer can predict fuel consumption, stability, structural stress, and hydrodynamic performance. The computer can optimize designs by running millions of simulations. What took months of physical testing can now be done in days on a computer. The designs are more optimal and tested more thoroughly. Design standardization has increased. Many modern ships follow standardized designs. A shipyard might build 10 identical ships for the same company. The standardization reduces design costs and construction costs. The shipyard becomes very efficient at building the same design repeatedly. The repeated construction means continuous improvement. The 10th ship is cheaper and better than the first ship. Standardization was less common in earlier eras because each ship was often unique or slightly different. Supply chain integration has changed ship design. Modern ships are designed to work with specific port equipment. The containers are standard sizes that match port cranes. The ship's dimensions are designed to fit in standard dock facilities. The ship's draft is optimized to use rivers and channels efficiently. The entire system of ship and port infrastructure has been optimized together. This integration wasn't necessary in the old era when each ship handled its own cargo. Speed has become less important. Old ships competed on speed. Being faster meant arriving at the destination sooner and being able to do more voyages per year. Modern container ships have relatively low speeds. The largest container ships cruise at around 19 to 22 kilometers per hour. They could theoretically go faster, but faster speeds consume much more fuel. The economics of shipping have changed so that slower speeds at lower fuel consumption are preferable to faster speeds at higher fuel consumption. Ship design reflects this change in priority. The role of the captain has changed. Old ships required captains with extensive training in navigation and cargo handling. Modern ships require captains who understand automation and computer systems. The captain still makes critical decisions, but the day-to-day operation is far more automated. Ship design reflects this change. The bridge is now filled with computer screens and automation equipment rather than analog gauges and mechanical controls. The navigation is done by GPS and automated systems rather than by manual calculation. Global supply chains have shaped ship design. Modern ships are optimized for specific routes. Ships operating in Southeast Asian waters might be designed with shallower draft to navigate rivers and shallow ports. Ships operating on the Atlantic might be designed for seaworthiness in rough ocean conditions. Ships operating in the Mediterranean might be optimized for speed. The design reflects where the ship will operate. In the old era, ships were more general purpose because supply chains were less specialized. The future of ship design will be shaped by decarbonization requirements. International maritime regulations require ships to reduce carbon emissions. Future ships will likely use hydrogen fuel cells, ammonia engines, or other zero-carbon fuels. These fuels require different engine designs. Hydrogen requires specialized storage systems. Ammonia is toxic and requires different safety systems. Future ships will look different because they will need these new systems. The design evolution will continue as technology and regulations change. Alternative propulsion systems will drive design changes. Some future ships will use wind assistance through sails or kites. Some will use nuclear propulsion. Some will use advanced battery systems. Each of these propulsion methods requires different designs. A ship with nuclear propulsion will need lead shielding and specialized containment systems. A ship with sail assistance will need mast structures. The ship's design will evolve to accommodate these new propulsion methods. Ship design reveals the principle that form follows function. As the function of ships has changed, the form has changed. Containerization changed the function from carrying diverse general cargo to carrying standardized containers. The form changed dramatically to reflect this new function. Automation changed the function from requiring large crews to requiring small crews. The form changed to eliminate crew accommodations. Environmental regulations changed the function to require emission control. The form changed to accommodate scrubbers and alternative fuels. Modern ships are built differently because their function is fundamentally different from old ships. The next time you see a modern container ship, understand that its design represents decades of refinement and responds to specific economic and regulatory requirements. The flat deck covered with containers, the forward bridge position, the wide beam, the efficient hull shape, the automated systems, all of these design choices are there for specific reasons. The ship is optimized for containerized cargo in a complex global supply chain. The ship is designed to minimize fuel consumption and operating costs. The ship is designed to meet environmental regulations. The ship's design is the product of hundreds of engineering decisions, each made to optimize some aspect of performance. If you're fascinated by how function shapes form and how engineering responds to changing requirements, subscribe to the channel. We regularly explore how design principles apply to real-world systems. From ships to aircraft to buildings, design reflects the system's purpose and the constraints it operates under. Understanding design principles reveals how the physical world is shaped by human needs and technological possibilities. Your subscription supports the creation of content that explores these design principles. Thank you for watching and for your interest in understanding how the form of ships reveals the function they serve in modern global commerce.